Hi grade 11s, today we're going to be doing a past paper questions on electrostatic. So let's jump right in. Here we have three identical spheres, A, B, and C, and they're all placed on plastic stands as shown in the diagram. The charge on sphere A is 5 nanocoulombs, sphere B is negative 8 nanocoulombs, and C is neutral. In terms of what that means for our charge, that would just be 0. The three spheres are brought in contact with each other and then separated. So if you think back to the theory of this type of question, of this entire topic, when you have differently charged objects and they touch each other, they have a transfer of that charge, that transfer of electrons. So that's what they're hinting at in this scenario, right? So if we take a look at the questions, 7.1, they ask us to calculate the net charge on each sphere after separation. So the way we would attempt this is by using the formula that the net charge is equal to the sum of all the charges divided by the number of charges that we have. So we would have the charge of A plus the charge of B plus the charge of C, all divided by 3 because there are three different spheres, right? So let's sub in the respective values. So for charge A, they told us that it's 5 nanocoulombs. So if you remember, whenever we're working with electrostatics, we ideally want to have all of our charges in coulombs. So we have to do all of our conversions. So if you don't remember your conversions, I'll just write them here in the corner. So when we're moving from millicoulombs to coulombs, we're going to multiply by 10 to the negative 3, right? If we have microcoulombs, it's going to be times 10 to the negative 6. If we have nanocoulombs, it's going to be times 10 to the negative 9. And then picocoulombs is times 10 to the negative 12. So they all go up in 1,000. So you kind of just need to remember that. I would suggest maybe writing this out at the beginning of all your tests and whatever, just to remind yourself of the conversions so that you don't accidentally make errors later on in the test. So going back to the question, we have 5 nanocoulombs. So to convert that to coulombs, we're going to say 5 times 10 to the negative 9. We're going to add negative 8 times 10 to the negative 9, because that is the charge of B. And then the charge of C, like I said earlier, would just be 0 because it is neutral. So it doesn't have a charge, right? And we're going to divide that all by 3. When we add all of that and divide it, the answer that we get is negative 1 times 10 to the negative 9 coulombs, right? So that means each sphere, now after they've touched and then been separated, all of them hold a charge of negative 1 times 10 to the negative 9 coulombs. Cool. 7.1.2, they ask us then to calculate the number of electrons in excess or deficit on sphere C after the separation. So we know that on sphere C it's going to have an excess of electrons because it's negatively charged, right? But now we just need to go about calculating it. So the formula that is appropriate here would be N is equal to Q over QE, right? So that is the number of electrons that we're working with is equal to the overall charge divided by the charge of an electron, right? So we have our charge, which is negative 1 times 10 to the negative 9. That's what we calculated in the last question, and divided by the charge of our electron, which is a constant, which is negative 1.6 times 10 to the negative 19, right? We divide those two, and then we'll get an answer of 6.25 times 10 to the 9 electrons. So that is the number of electrons that were transferred to sphere C. Okay. The spheres are then placed a distance apart, as shown in the diagram. So you can see that the distance between sphere A and sphere B is 15 centimeters, and the distance between sphere B and sphere C is 20 centimeters. They then ask us to draw a vector showing the electrostatic forces acting on charge B due to the presence of A and C. The first thing you need to ask yourself is what type of forces is being exerted on sphere B, and because they all have the same charges, they're all negative 1 times 10 to the negative 9 coulombs, so they're all negative. We then know that there's going to be force of repulsion between all of the spheres, right? So in terms of the force that A exerts on B, that will be to the right, because there's that force of repulsion, it's pushing it away. And then in terms of the force that is exerted by sphere C on sphere B, that would be to the left, because again, it's pushing it away because there's that force of repulsion, right? But now for this question, you have to account the distances. If you think about the formula, F is equal to K times Q1 and Q2 over R squared. This is telling us that the relationship between our force and our distance is that they're inversely proportional, right? So the greater the distance, the smaller the force. Therefore, if we were to look at the relative distances between A, B, and C, we know that the forces would not be of equal magnitude. They will be different because they are at different distances from each other. Because A and B are closer to each other than B and C are, we know then that A will exert a stronger force on B than C will exert on B. So in terms of how our vector diagram would look, our sphere B is this dot. We know that A is exerting a force to the right, so we're going to draw that arrow in there. So this is FA, and then FC will just be in the opposite direction and slightly shorter. And let me just emphasize again, the reason why C will be shorter is because there's a greater distance. And if there's a greater distance, then there's less force exerted. Okay, so FC. So that will be what our vector diagram would look like. Then they ask us to calculate the net electrostatic force on sphere B. So the way we do that is we're going to calculate the force that is exerted by both A and C, and then we'll calculate the F net. So we'll use that same equation I brought up earlier. So force is equal to K times the charge of, let's say, A and the charge of B over R squared, right? So K is our constant. We know it's 9 times 10 to the 9. We then have the charge is -1 times 10 to the -9. And because the charge of A and B are the same, I'm just going to square that, right? We then put that over the distance, which in this case is 15 centimeters. But remember, you always try and get it in your SI unit. So we're going to convert centimeters to meters. And to do that, it's going to become 0.15, right? And then I'm going to square that. So I do all those calculations, and I'm going to get 4.00 times 10 to the -7 as my answer for the force of A on B, right? Then I'm going to do the same thing for C. So QB and charge of C over R squared. So 9 times 10 to the 9, -1 times 10 to the -9 squared over, but now we're using a different distance, which is 20 centimeters, which will just become 0.2. And we square that, and then we will get an answer of 2.25 times 10 to the -7, right? Then in terms of calculating our net force, that's just going to be the force of A plus the force of C. Force of A plus the force of C. But remember, they're acting in different directions. So we need to choose a positive direction. For this case, because I know the force is going to be to the right because F is larger than C, A is larger than C, I'm just going to choose right as my positive direction, right? So then I'm going to have 4.00 times 10 to the -7 plus -2.25 times 10 to the -7. It's negative because it's in the opposite direction. And then my answer will be 1.75 times 10 to the -7. And because it's forces, my answer will be in newtons. And remember, I also need to give a direction, and in this case, it will be right. Cool. Thank you so much, grade 11s. That was the past paper question on electrostatics.